This video guide is going to show you how to do a relatively simple principal component analysis in SPSS. What this data is looking at is different forms of intelligence. So a researcher recruited 237 individuals and got them to complete 5 different forms of intelligence tests. So you can see participants completed a logic puzzle, a shape rotation task, a shape sequencing task, a sentence completion task, and a numerical sequence task. And what they're interested in is whether these tests are tapping into the same or different forms of intelligence. So in order to explore this, a principal components analysis is run on the data to see if some of the measures are measuring a very similar concept and other measures are measuring other unrelated concept. So all the scores completed here were standardized as a score out of 7. There's actually quite a good reason for doing this, simply being that if you had one of these that was scored on a scale of 1 to 100, for example, then this can be a little bit problematic for the principal components analysis, and particularly if you are analysing using a covariance matrix, which I'll come on to later, this could overwhelm the principal components analysis. This is less of a problem if you analyse the correlation matrix, which again I'll show you later on, but still it's always quite a good idea to have things measured on a relatively even scale. Sometimes people standardise all scores before they run any analyses. So to run a principal components analysis in SPSS, you just go to Analyse, and then to Dimension Reduction, and then Factor. Principal components analysis comes under Factor Analysis. Really straightforward menu. We don't have to worry about the selection variable at all. We just need to put the variables in which we want to do our principal components analysis on. So simply, we just click across all these variables and we're telling SPSS these are things we want to do our analysis on. There are lots of options, however, that we need to look at. So we click on descriptives. So for descriptives, we keep initial solution ticked. This is just basically going to say the factors that had eigenvalues lower than our cutoff, and the cutoff we're going to use is 1. It's still going to show those for us in the data set. We want univariate descriptives. This gives us descriptive statistics, means standard deviations for each of our variables in the analysis. Coefficients, we want coefficients. This will just give us our correlations between these variables as well, which are quite useful to view. We really need to tick this box. This is very important. The KMO stands for Kaiser-Meyer-Olkin measure of sampling adequacy, and basically we want this figure, the KMO, to be greater than 0.5 to have an adequate sample. The other measure, Bartlett's test of sphericity, this tests the assumption that correlations between our individual items are sufficient for a PCA, and essentially we want this to be statistically significant. If we click continue there. If we look at extraction, now you can see that principal components is default. It does other things as well, different sorts of ways of doing it, but we're doing a principal components analysis, so we keep it fixed as this. How it does the analysis can be based on what I mentioned earlier, the correlation matrix or the covariance matrix. Basically this is just standardized. All the variables are standardized. It wouldn't make a huge difference in this data set if we used either of these two, because everything's scored from 1 to 7. But as a general rule, people tend to use the correlation matrix, and that's what we're going to be sticking with today. We keep unrotated factor solution, and we also ask for a Scree Plot. This can be a very useful way of visualizing data, and actually is very commonly used as a way of ascertaining how many different components you have within your data set. Now, this is the extraction bit, and this is really important. This basically is the cutoff for what eigenvalue represents a important component or important factor found in your data set. 1 is the default, and 1 is what's known as Kaiser's rule, and this is very commonly applied. Though you don't have to use Kaiser's rule, there are other examples. For example, it's been argued that for a principal components analysis, the eigenvalues greater than 0.7 is better because an eigenvalue of 1 or more is too conservative, particularly if we expect there to be independence of certain measures. So if we think something's going to be very, very different than other measures, then we may want to have lower eigenvalues as a cutoff. This here, fixed number of factors to extract, is where you tell SPSS that you want a certain number of factors to be produced from your data set. This can be used and is used if you do what's called a Monte Carlo simulation, for example, beforehand. And a Monte Carlo simulation gives you an estimate of the number of factors that exist in your data through simulating your data set. And say, for example, a Monte Carlo simulation said you've probably got about 5 factors, then you just put 5 in here and it would produce a 5-factor solution to your data. However, generally speaking, we're going to you let your principal components analysis tell you how many factors you're likely to get. And in this case, we're going to stick with Kaiser's rule and we're going to have eigenvalues greater than 1. This is the most common thing that appears within the literature. Click continue, and then we've got rotation. So basically what the rotation does is allow you to produce simple and interpretable factors. If you don't use rotation, it can be really inaccurate when you are looking at what variables load onto each factor. It can be really confusing, and usually if you don't do a rotation, you have one incredibly dominant factor and then any other factors tend to have a very small number of items on them. So we often use a rotation in order to produce clearly interpretable outputs. The two ones that are commonly used are varimax rotation and the direct oblimin rotation. This is referred to as an orthogonal rotation, and it's used when factors in the analysis are assumed to be uncorrelated, and it's the most commonly used. The oblique rotation, so the direct oblimin, which is an oblique rotation, this is commonly used when you expect your factors to be correlated with each other in some way. This is completely theoretically driven, and you have to choose the correct one according to what you know about the measures you're using. In this example, we're going to use a varimax rotation. And click continue, and then we just click OK. So this is the output. First of all, it says factor analysis at the top, but it is a principal component analysis. So the first thing that appears is your descriptive statistics table. So you could use this to write up a descriptive statistics section in any report or paper you were doing, and you'd want to format it something like this. Again, it always gives it to lots of decimal places that you shouldn't be doing. You don't need to write this, it's the same for everything. We've got a sample until the 37, so there's no point writing that for each measure. Next thing is the correlation matrix. This just shows you a Pearson's correlation coefficient between the variables. Doesn't give you a p-value or anything like that with it though. Like all correlation matrices, it does everything twice, and it correlates everything with itself. So logic puzzle versus logic puzzle, correlation of 1. Shape rotation, correlation of 1, and so on. So we need to look at half of this table if we're going to look at it, and this shows us what the associations are between the individual variables. It gives you some idea already of what's going to be correlated with what. So for example, logic puzzle and sentence completion are highly correlated with each other, but logic puzzle doesn't seem to be highly correlated with anything else. So for looking from this, you can probably make an estimate that logic puzzle and sentence completion are going to fall onto the same component. So you could again use this to write up some, if you want to do a correlation matrix for your descriptive statistics. This next table is very valuable because this tells you basically if you met the assumptions of the test, are you able to do a principal components analysis. So for the Kaiser-Meyer-Elkin measure of sampling adequacy, we want that to be greater than 0.5 as it is, so we know we've got a sampling adequacy. Bartlett's test of sphericity, again, we want this to be statistically significant, and as you can see, we've got a very highly significant result. People often ignore this when they're reporting it. They certainly used to, it's becoming a lot more common these days, but it certainly should be reported so the reader can see that you've met these two assumptions, and you can just format it like thus. We don't really need to look at the communalities table at all, so we can just ignore that for now. This is the first really important table that's come out of our principal components analysis. This is what's telling you how many components are in your data set, or how many factors and components being used interchangeably. So if you recall, we set our eigenvalue for extraction as being 1 or more. That was Kaiser's rule. So basically this is saying is that any eigenvalue that is greater than 1 is a important component, an important factor. It's something that statistically meaningful. If you can see here, this indicates that we've got a two-factor or two-component solution to our data. Component number 3 is lower than 1, as is 4 and as is 5, so we've got a two-component data. The other thing that's important, this table gives us some very useful information. Component 1 accounts for about 40% of variance in the data. Component 2, about 27% of variance in the data. And overall, the cumulative amount of variance the two components account for is 67% of variance in the data. What we can say is from this is our data showed that there's a two-factor solution, two-component solution. These two components predicted 67.46% of variance in the data, with component 1 predicting 40.30% of variance and component 2 predicting 27.16% of variance in our data, and we can just write this up accordingly. The next thing we can look at is the Scree plot. The Scree plot is just basically a graphical representation of these figures here. So the eigenvalues for the component number are plotted. The reason it's called a Scree plot is because it's meant to look like scree from a mountainside like this. And basically what this does is it tells you the number of factors that you probably have in your data set. So basically what we can look at is say we've probably got a two-factor solution. Firstly, this is the cutoff line, and there's only two factors above the cutoff line. But the other thing as well is the slope for at 3, 4 and 5 is relatively flat, whereas the slope is really steep down to the point of 3. So this means that the ones on the steep slope represent probably important factors or components. So in this case we've got 2 on the steep bit of the slope, so that means we've got a two-component solution. But essentially it is a graphical representation of these numbers. So we know from this data that we have two components to our data. This is only half the story, of course. This just says there are two components in the data. It doesn't tell us what variables make up this component, and that's a really, really critical thing, because it's all very well saying, oh, these 5 measures of intelligence make up two components, but that's no use to anybody. We need to know, okay, well, which ones make up component 1, which ones make up component 2, and what are those components? We need to give them a name of some sort. We need to have some justification for why these two things are components. So we need to look at our component matrix here. As you can see, it's produced 2 of them. We've got a standard component matrix and a rotated component matrix. We don't really need to analyse this one, but it does really highlight the importance of rotation. Essentially, the numbers in both of these things are correlation coefficients, and what these numbers actually represent is a Pearson's correlation between the individual item and the component itself. So because we've got a two-factor solution, we've got 2 components appear here. If this produced a 3-factor solution, let's say that was 1.02, for example, then this would produce another component here as well. But because this has showed us 2 components, this also gives us 2 components. So, as I say, these are just the component loadings, and you can have a positive or a negative loading. Obviously, a positive loading means that high scores on that load very highly on that component. If it was negative, it would mean high scores load very low on that component. So I'll come back to this table in a moment, but this is the table. The rotated component matrix is the one that we interpret. As a general rule of thumb, and is very commonly used in the literature, if you have a loading of 0.4 or more, this means that it is significantly loads onto that factor. Of course, you could just use a correlation coefficient table, which will tell you whether these individual correlation coefficients are statistically significant anyway, because we can just say, well, this is a Pearson's correlation coefficient, here's our sample size, is that a statistically significant correlation coefficient at sample size? And that's a perfectly valid thing to do. I've done it myself when I've done papers using such analyses. However, you just need to be a bit careful, because we know as sample sizes get bigger, the more likely something is to be statistically significant. So if you have a very large sample size, then a very low factor loading could actually be statistically significant as well. It is possible for things to load onto more than one factor as well. It doesn't seem to be the case within this data set, but that's perfectly possible. Something could tap into two underlying factors. So if you look at this table, it's pretty straightforward, a pretty clear-cut thing what loads onto what. Basically, as you can see, if we use the 0.4 rule, anything above 0.4 can be viewed as being a significant loading onto that component. We can see component 1 is made up of the shape rotation, shape sequencing, and numerical sequencing as well. Factor loadings for logic puzzle are low on component 1, and sentence completion are also low on component 1. If you look at component 2, that's made up of our logic puzzle and sentence completion, two very high loadings on that, and the other three have low loadings on that. So we can see component 1 is made up of 3 factors, component 2 is made up of 2 factors, and we can tabulate these results. It's really nice and clear to tabulate these results, and it makes it very easy for the reader to see what is making up each component. Now, this does highlight the importance of rotation, because if we look at that, we've got some nice clear-cut thing. We've got 3 factors load onto component 1, 2 onto component 2, nothing loads onto more than one factor. There's no really high negative loadings or anything like that, it's all really clear-cut. But if you look at the component matrix before any rotation, you'll see everything significantly loads onto factor 1 positively. And then if you look at this, you can see we've got a high logic puzzle, high positive loading onto that. Sentence completion, high positive loading, but we've also got very high negative loadings and numerical sequence as well. So it doesn't make a lot of sense to look at this and go, well, everything loads really highly onto one factor. So it's never really that good an idea just to interpret a component matrix. We want to look at our rotated component matrix. Once we've done our table for the rotated component matrix, we can also write up a brief description of what it shows for the reader, and also we can name our components by looking at what the variables are. We can come up with some sort of idea what the overarching construct that we're looking at, and just write that up accordingly, so it's very clear to the reader what makes up what components and what you have called the component. This section of the video is going to quickly show you how the output would look if you were to do a different form of rotation. So if you were to do an oblimin rotation, because it does give you slightly different tables, but the interpretation of them remains the same. Just do the change quickly. So we just go to rotation, we're going to have a direct oblimin, leave delta as 0, and we click continue, and then OK. So the output is relatively similar. Indeed, it's completely identical when it comes to the eigenvalues and so on. That aspect of it doesn't change, nor does sampling adequacy. The only thing that changes is the factor loadings, and you can see how it changes. It's got the standard component matrix, which we discussed earlier, but now it's got two. It's got a pattern matrix and a structure matrix. Generally speaking, it is the pattern matrix that is interpreted. And as you can see in this case, it makes no difference to the outcomes at all. Shape rotation is factor 1, as is shape sequencing, as a numerical sequence, and factor 2 is sentence completion and logic puzzle. So there's no change in the outcomes, and you write it up in exactly the same way. The structure matrix is very rarely reported actually, but as you can see in this case, it's pretty much exactly the same pattern results anyway. I would recommend maybe you'd write up the pattern matrix, but it may be worth just checking the structure matrix. If the structure matrix differs a lot from the pattern matrix, it may be indicative of some problems within your data set that some other solutions may be required. to look at. However, generally speaking, as I say, it's the pattern matrix that you will be reporting if you were to write this up, and you just report in exactly the same way, except you just make the statement below the table that the oblimin rotation was used.